So today I'm going to try and show basically an immediate application of these of Rowow's cation exchange membrane for the separation and concentration of neodymium in a dissolved neodymium magnet solution. So this is some sulfuric acid that has some neodymium in it that I dissolved a while back. It's got a little bit of precipitate in there already, and that's because neodymium has an interesting property in sulfuric acid solution where it's got inverse solubility with respect to temperature. So normally things become more soluble as you up the temperature. Think dissolving sugar or salt in water. If you up the temperature, it's going to dissolve better. But here, if you up the temperature, the neodymium will actually start precipitating out. And so that's what happened here a little bit. But I should still have enough in this solution, just judging by the color even, that there's still neodymium in here, and more importantly, there's a bunch of iron in here as well. So we're going to see if we can use this cell setup to actually plate off iron and at the same time concentrate the neodymium more at the cathode side. Let's do, and part of the experiment here is going to be to see how well my 3D printed cells stand up to the solution, because it's PET G, and I really am not sure about how well this is going to survive. So there's 35 milliliters there. We'll do another 35. Okay, we've got a bit left here. Cells are filled up and ready to go. Doesn't seem like it's immediately reacting with the cell or anything like that, so that's good. All right, I just had a little thought of, just in case this starts failing and the cells start degrading or something and we spring a leak, just have some secondary containment. That should help. Okay, so we have the anode and the cathode set up here. So the idea is you have, right now, it's technically three main constituents. There's boron, there's iron, and then there's the neodymium. The boron we're not really looking at for this, but what we're going to do is we're going to force iron and the neodymium cations to go this way towards the cathode through the cation exchange membrane. But the anions, the sulfides and all that stuff, aren't going to be able to make that movement. So the idea then is that the electric potential here will cause all the cation, or a lot of the cations, to slowly move in this direction, effectively upping the concentration of cations in the cathode cell and depleting the concentration in the anode cell. At the same time as that's happening, hypothetically, the iron should start plating out and precipitating on this side. I'm not sure if it's actually going to plate out or precipitate or what, but the iron should drop out in solid form at the cathode side. So you get a 2-for-1. You get an iron separation out, and you get a solution with an enhanced concentration of the neodymium than what you started with. Okay, so I'm just gonna set the current to 1 amp and set the voltage to 10 to start with, and we'll see how it does. This membrane has sat pretty much since the last time that I did that demonstration with this exact setup in the last video, so we'll see how it behaves. It looks like it's actually doing quite well. I might turn this amperage down a bit just to make sure that I'm not overdriving the system too much. Make sure that these are bottomed out. Okay. Okay, I've got this filter set up here. This is just a regular kind of soldering filter. It's kind of loud, but this should help capture any nasties. This shouldn't produce too much weird gases. Like, there shouldn't be any, you know, chlorine coming off of here or anything like that. I think mainly it's going to be hydrogen at the anode and I suppose maybe oxygen at the cathode. I'm not sure, but yeah, just have this running just in case, because I'm going to let this run for a while. 2 reasons: to get as much of a concentration effect as I can on the cathode side versus anode, and then also to kind of test out how the cell, how this PETG 3D printed material behaves with this specific solution under these electrolysis conditions. Okay, it's been about 30 minutes. Still no sign of any issues. I did a little temperature check with this IR camera, mainly just to look at the electrodes, and it looks like the anode is warming up ever so slightly, not too much though, about 29°C. I don't know how well this is gonna come across on camera, but no heat issues yet, which is kind of what I was worried about with turning up the amperage. But I think I can turn up the amperage even more. But first, let's check and see how the insides look here. Turn the power off. So there is something, it appears, that's on the anode. Might be iron sulfate, maybe something like that, not sure, but definitely the anode solution is very kind of murky and brown. And the cathode is, yeah, I'm pretty sure that's some kind of maybe rust, but the cathode is a lot pinker for sure, less murky too. Looks like we're plating off some kind of iron something on the cathode, so that's interesting. Okay, so I'm gonna go ahead and see the voltage really is dropping quite a lot to keep that half amp going. So I'm gonna increase the amperage even more here. Actually, first I'm gonna turn the voltage down just to limit it in case it runs away or something weird happens. And then I'm going to go ahead and turn up the amperage quite a bit here to 3/4 of an amp. Let's see how that goes. Well, this first electrolysis run did not go quite as planned. Unfortunately, the anode side degraded quite a bit, and a bunch of carbon compounds basically went into solution from the graphite anode degrading. So I redid this with a platinum anode instead, and that worked a lot better. You will see that next. I made a fresh solution of dissolved neodymium magnet and some 3 molar sulfuric acid, and electrolyzed some again, but this time I used a platinum electrode on the anode side, so that way a bunch of carbon isn't being deposited into the solution. And there's a definite kind of color difference now after running it for about 2 hours, a little over 2 hours. Now I'm at 1 1/4 amps. It's definitely warming up, but you can see, you know, purple-pink color with the cathode side, and the anode side is turning kind of brown, almost rust color, probably due to iron in there, I would guess. But the interesting thing is that basically, I'm not sure why it's preferentially leaving the iron behind or what. Well, we'll scan this on the UV-VIS, but this is telling me that this side is being definitely depleted in neodymium. It's likely being depleted in both neodymium and iron, but maybe because there's more iron in the solution, because the magnets are, I don't know, like 70% iron, that what's left behind here right now is mostly iron due to the higher start of iron, and so you're seeing that kind of rust color. And then this side is getting more purple and pink. And I did kind of dilute these by half to see if I could get the effect to be more pronounced when starting. So basically I put 15 milliliters of the magnet solution in each cell, and then topped it off with 15 more of just pure water, deionized water. And that's to see if I can get a more pronounced effect, because starting with like a very concentrated solution might be harder for me to pick up the effect on the UV-VIS. But based on this, just by eye color change alone, this is very promising. The pH strips aren't really indicating much of a pH strip or much of a pH difference. They're both showing pretty much, you know, on the acidic side, somewhere in the 1 to 2 range. I'm guessing it's because the starting solution is so acidic that it would take me a while to push enough cations to the cathode to actually get a detectable pH differential just using the strips. We probably would be able to see it while using like a, you know, proper pH meter, but I don't really see it with the strips. So I'm gonna stop this and withdraw some of the solution, make some samples, and run it on the UV-VIS, see if we can get kind of a successful enrichment here. I'm still not getting a deposition at all on the cathode side. Yeah, it doesn't really look like the iron is depositing or precipitating. And I think likely that's, likely that's due to the fact that I can't get the pH high enough locally for the iron to precipitate out, because basically what happens with this is if the pH gets just high enough in a local region, then the iron in that region will precipitate out of the solution, and the reaction just kind of keeps going while the bulk remains acidic and keeps the neodymium in solution. Because if you raise the pH enough of the bulk, everything will precipitate out, iron and neodymium. In fact, that's normally how you can control this separation, is just by pH adjusting with like lye, some NaOH or something like that. And if you do it precisely enough, you can basically get the neodymium, I think, to drop out first, and you can get a clean separation that way. I would need to, the second run was fairly successful here, where I used a platinum anode. Didn't really corrode at all as compared to the graphite anode, which got eaten up pretty badly. But yeah, and then still a graphite cathode, which stood up just fine. I still didn't really get much precipitation, unfortunately, so that's something to work on, but I got a pretty clear difference between the cathode and anode. Here's the solutions I collected, about 30 milliliters of each. Interestingly, the anode actually lost a lot more, I don't know, maybe like 5 milliliters of volume, something like that. And the cathode actually gained a little bit of volume in liquid, so the levels between the cells dropped when I was collecting. I'm not sure why that is. Yeah, I'm not totally sure on that, because I would assume that levels would deplete somewhat evenly if water is dissociating and then basically, leaving as gas in the form of hydrogen and oxygen on either side. I would assume kind of an equal amount of dissipation, although maybe if the anode was depleting a lot more, it's at the anode side that oxygen should be leaving from the electrolysis, and then at the cathode side hydrogen is being generated, and then hydroxide groups are left over from that, which get left in solution. So maybe it's actually because on the cathode side you have the hydroxide groups left behind in solution, whereas on the anode side you have the protium, so the hydrogen ions left behind, which then go over to the cathode side anyway, through the membrane, and so they get pumped over, and they probably recombine at least somewhat with the hydroxide groups, generating more water, and so you get this imbalance. So that could explain the volume difference. I'm not totally sure. I'm still a bit iffy on this stuff. This isn't really something I've gone too deeply into in the past. But anyways, point is we definitely got a big difference between anode and cathode. The cathode side is still that nice kind of purple pink color of the original solution. It's a little hard to see in this light, but you can see the pink kind of coming through. And basically the cathode side retained that. Now it's a little lighter from the get-go because I diluted both cell sides down by a half. So I took 15 milliliters of the original solution and then diluted with another 15 milliliters of water just to get a more pronounced effect. But yeah, so cathode side nice and pink, which is what we would want and expect because it's keeping all the cations and attracting them. And then the anode side went kind of clear, like almost yellow brown, but I don't know how easy it is to see that difference through the camera. Maybe if I turn these a bit like this. Yeah, I mean, you can see a very clear color difference. And this comes through, actually, I'll show it here in a minute. We'll go look at the UV-VIS spectrums. But we clearly, through the use of this cation exchange membrane, moved definitely neodymium. I don't know about iron, but neodymium for sure moved towards the cathode and out of the anode side, because the color difference alone tells you that right away, because neodymium has neodymium sulfate in this case, but nitrate as well, similar thing. It's got that characteristic kind of pink, light pink color to it in solution. Okay, so now we just load this guy in. Here's the spectrum, the UV-VIS spectrum of the cathode and anode solutions captured here. And the interesting thing, so first of all, I subtracted the scanning plate background, and that's basically just the plastic of the plate has its own spectrum, mainly over here in the UV region, and if you don't subtract that out, you just get a lot of stuff on the UV side, so you can't really see what's going on with your sample. Preferably you would get something that's totally transparent across the whole spectrum. Something like quartz, at least in this range, is pretty much fully transparent. Unfortunately, I don't have a quartz plate to do this with on this reader, this microplate reader. But normally for like UV-VIS, the regular spectrophotometers will use like the quartz cuvettes with a 1 centimeter path length, and you fill them up and scan them. But anyway, so these are the background subtracted spectrums of both cathode and anode. And a couple of things that we notice right away here is that on the anode side, we have a much more pronounced, broader kind of peak. In fact, this is blown out. It maxed out the detector. And the challenging thing here is because I'm using a well plate that already has such a high absorbance in this region, it kind of messes me up on my dynamic range on this side, where I don't have very much room to read an absorbance value in this region. So if I have a sample that also absorbs strongly in this region, it just blows out, and I max out basically at a relative absorbance of 4 here. So this is just totally maxed out, but you see how much broader this peak is basically before the drop off. It doesn't start dropping off until somewhere around 375 nanometers, whereas on the cathode side we start dropping off around 316, 320 nanometers. And the interesting thing about this is that this pretty much exclusively, at least in this solution, has to do with the iron species. Iron 2 plus and 3 plus, I think 3 plus is the main one, but either way, iron cations are active sort of in this range of absorbance for UV. So this is promising and interesting because for whatever reason, the anode side retained a lot more iron, it seems, than got moved over to the cathode side, because they both started with the same amount, because they got, both sides got the same solution, but the cathode side seems to have relatively quite a bit less iron than the anode side. And one reason for this could be that the anode side did technically get reduced in volume, so whatever concentration it has went up, technically, from a volume standpoint. I don't know if that would have made this big of a difference. So this is something I need to look into farther, but based on this, we basically have an iron amount difference. So that's kind of weird, because you'd think that the iron would come right over through the cation exchange membrane along with the neodymium, but maybe this membrane that I made with the specific beads that I used has more of a selectivity for the neodymium. That could be. We know that in theory, the hydrogen ions should have a much, much easier time passing over towards the cathode through the membrane, because they're so small. But so maybe there's a membrane selectivity happening here that I just don't know about. But either way, we have a difference in iron. And another thing is this peak right here at 444 nanometers, which might still be here. It just might be getting sort of absorbed in this very broad peak, because there's a bit of a hump. That's to do with, I think, praseodymium. Usually there's some in neodymium magnets, so that's that one. And then you have kind of all the characteristic neodymium peaks. You have this pair, 512 and 522 in this case. You have another big one here, 577. It's another characteristic neodymium peak. You have another one at 740-ish. You have another one at like 790, and then another one out here at 860. But all of these are all of the characteristic neodymium peaks on the cathode side are higher in absorbance
than on the anode side. And basically that tells you that there's more of a concentration of neodymium on the cathode side than the anode side. So we pushed neodymium cations from the anode side to the cathode side and have effectively concentrated them on the cathode side, which is, kind of on the first hand, I didn't get any precipitation or anything like that, so this didn't really work all that well necessarily as a separation scheme as I was intending at first, because what I wanted was to see if I could just straight up, drop out the iron, precipitate it out on the cathode side, and be left with a relatively pure, neodymium solution where we just have the neodymium peaks. And that's not quite what happened, or it didn't happen at all actually, but we did concentrate the neodymium on the cathode side. And right away, an application there is in the rare earths industry, for instance, the concentrations that they start with when they're leaching the minerals for the rare earths are very, very low. And so, one of the first steps that you'd want to do is to get that concentration up to have a nicer solution to work with before you start the separation process, basically. And so, something like this could possibly be used for that application where you start out with a very, very dilute solution and you use something like this to concentrate your solution on the cathode side. Maybe another thing here is while you do this, you could also in parallel, as Rowow talks about, have a scheme where you're regenerating your acid leach. So I think this is a worthwhile uh, pursuit to try and come up with a sort of easy demonstration application of this membrane, because there's clear potential there, and I know that Rowow is already doing some application side things, but I would very much like to show a membrane-based separation of neodymium from this solution, or rather, purification of neodymium, because with all that's going on with the rare earth requirements and the critical minerals that I think DOE has put out, the call for critical mineral development strategies. This could be a very big deal for that. So I would really like to see if I can, show a very kind of low level prototype doing this with the neodymium magnets. And if any of you or anyone has some ideas on how a better way to try this for demonstration purposes, please let me know.